everybody. Welcome to our 3 p.m. talk, which is You Don't Need That. And this is our speaker, Christopher Neugebauer. And he came all the way from California to give us this talk. So let us welcome him.
Thank you. Thank you very much. This is not LVH's talk if you're reading the paper program. The only pickles you can find are at the deli across the street. Right, so this talk is called You Don't Need That. It's a discussion of design patterns and Python. My name is Christopher Neugebauer. You can tweet me at that handle, and that handle will also find my email address and various other things if you go looking for it. So first, a bit about me. I'm Australian, if you couldn't tell by the accent. I live in Petaluma in Northern California. And I run a small boutique one-track Python conference there called North Bay Python. Our CFP is currently open if you want to come along and talk at that, or just get along first weekend of November. I'm also a director at large of the Python Software Foundation, and I work as a software engineer at Shutterstock. And at Shutterstock, I work on a team that mostly codes in Python with a bit of Java or Perl thrown in when we're maintaining legacy services. But I often find myself working closely with a team that works primarily in Java. And that experience has led me to thinking about what I'm talking about today and what I'm hoping to share with you. And situations like my own are increasingly common. Development teams are increasingly polyglot organizations, especially now that we're writing quite heavy applications in web browsers. Teams might be working on JavaScript in the front end, but might be using Python with Flask or Django in the back end. Or in my case, using Python for back-end services and enterprise Java for orchestration stuff. And there's many ways that developers talk about different programming languages. They might talk about how rigid or flexible the languages are, or they might talk about the programming paradigm that they let developers express when they're using that language. They might be using functional programming or object-oriented programming. And then we have Python, which is it's a more flexible language than Java or C++, but it's also a lot less flexible than, say, JavaScript. And these days, it has features that make it as descriptive or as flexible as you want it to be. It lets you use object-oriented programming features like strong typing or classes, or functional features like first-class languages, and it has things all of its own, like generators or coroutines. And so Python doesn't really fit this sort of OO functional paradigm split that people often talk about. And so I've been wondering about how we discuss Python, how we think about using Python. And I saw a talk by Luciano Ramalho at PyCaribbean this year, and he explained a really great framework to think about this, which is that languages provide you with features that you can use to build your programs, rather than thinking in terms of paradigms. And so by thinking in the terms of a feature set your language can give you, you can make your programs expressive within the language that you're using to write those programs. Which brings us to the topic of design patterns, which is what I'm going to be talking about today. So design patterns are things that let you express ideas that are hard to express using the features that your own programming language has in a familiar way to other users of that language. The majority of common design patterns are object-oriented design patterns, and the most popular ones that are most commonly used are the ones introduced by the Gang of Four in the mid-90s, and they were written when rigid languages like Java and C++ were the best examples of object-oriented languages that are out there. And so the majority of popular design patterns tend to fix issues with expressivity that occur in C++ or Java or languages like that. And so today we're going to write some implementations of common OO design patterns in Python, firstly as if we'd implement them in another language. Then we're going to look at how we'd implement them if we were implementing them in Python. And then we're going to look at features that we can use in Python that let us avoid using those design patterns entirely. The end result is that we'll have code that makes the best use of Python and helps you come up with ideas on how to port code or ideas to Python without simply transliterating your code. But more importantly, understanding why certain design patterns are necessary in other languages means that you can communicate with and work with developers who use those other languages far more effectively, be that through developing better Python code or being better able to understand why non-Python code is structured the way it is when you're working code bases in other languages. So we're going to begin with the absolute most simple design pattern that there is, the singleton. So the singleton is a class that can only be constructed once. So you can construct one, there's only ever a single instance of it. So if we were writing Java code in Python, our singleton would look something like this. There's a definition of the class up the top. It has an attribute, some data, and then we have an accessor function which checks to see if we've got an instance and constructs the instance if we don't, and then returns that instance. So calling that will always return the same object. And this code is already pretty complicated, and it doesn't look like I would write code in Python if I were writing code. There's this if instance is none, which is sort of not how we do things in Python. It violates the easy to ask forgiveness and permission rule. So let's see if we can implement this even more Pythonically. And you can. We've got the same class up here, but instead of the accessor method, we're explicitly constructing the instance at a module level and then deleting the constructor so that future callers can't see it. And this works. It's perfectly reasonable, and there's only ever going to be a single instance of that. Yes, there are ways around this because Python lets you do that, but most people won't go looking for it. Yeah, leave questions to the end. So then you can access the data from the instance just as you would, accessing it from a module or whatever, and you also can't call the constructor a second time. So you can implement singletons in Python just fine. You can implement it as if it's Java or C++ code, and you can even implement it in a way that looks Pythonic without existence test or without accessor methods. But instead of doing that, you can stop and ask yourself a question. Why would you do this? And to answer that, you need to answer another question, which is, what exactly are you trying to achieve by doing this? And so singletons exist because you need namespacing in pure object-oriented languages. And singletons give you a way to namespace related functions and data. You can put all the related data, all the related functions into the same class and make that class a singleton. You'll only ever have one instance of it. But Python already has pretty good namespacing functionality. The other reason is so that you can pass the functionality around to other functions. A singleton might be a derived class of some base class. So you can have two singletons with the same interface, but clearly different data, and you can pass those into a function that takes that interface and does something with it. So here's what we need. We need to prevent multiple constructions so we can't have multiple versions of the object, and we need to be able to pass our object as arguments to a function. And it turns out that Python already has a feature built in that lets you do this. And that feature is the built-in module system. So let's look at why this works. First up, in Python, almost everything is a variable. Now, when I say almost, I mean that anything that holds data or functionality is a variable. And what this means for you is that class instances and modules look more or less exactly the same once you start passing them around to different functions. So instead of defining classes to hold all your data with a given structure, you can instead define a series of modules which have the same attributes and the same functions that hold the different or have the different references that you need. And you can pass those modules around in exactly the same way as you could as if they were class instances. And you probably already know by now is that if you import something multiple times from within the same program, you always end up with exactly the same object, no matter how many times you import it. Even if you delete all the references to it, it sticks around. So modules do both of the things that we want. It prevents multiple construction, and it can be passed as arguments to functions. So in summary, you don't need this pattern in Python because the module machinery that's built into Python does it all for us. And it does it all in a more expressive and familiar way to Python developers. Right, so following on a similar line, we're going to look at a technique called dependency injection. And a dependency injection is an extremely popular thing in Java, to the point that there are giant frameworks out there just to do dependency injection automatically for you. And the basic idea is that you provide dependencies to classes as you construct them, rather than the classes going and finding the dependencies as they need to use them. Ironically, these dependencies often turn out to be singletons, in case you want a clue as to where this section is going. It's not all going to be like this, I promise. So the best way to illustrate this is by operating in reverse. This is very similar to how the mail system in Django works. Say you want to create a mailer object that retains some sending address so you can send lots of emails by passing this object around. So you pass in your from address and then you have this send function which calls the send mail that we've imported from some library. So that's it without dependency injection. And the version with dependency injection looks a bit different. So this is implementing it as if it were Java. Rather than directly importing sendMail, what we do is we pass in an object that we store in our own class at construction time. So this mail sender thing here is the dependency that we are injecting into the class. And then when we want to send a mail, we call the method that's on the dependency. So this version is very strongly object-oriented, and I've written it this way as a necessity based on how Java's worked historically. You can't pass functions around in Java, but you can pass functions around in Python, and so this is how it would look if you did it just using functions as your dependencies. So I'm passing in this sendMail function, and then we can call sendMail without needing the intermediate dependency. But this is still not nearly as Pythonic as importing the function you want and calling it directly. And just to remind you, this is what that looks like. So why would you write it with dependency injection? People who write Java code for a living could write their code just like the slide where I'm, the previous slide that I showed you, importing the function that they want, calling the function directly. But generally, Java developers don't do this. So let's talk about why you would want to write things with dependency injection. And the answer to that is testing, and specifically the answer to that is unit testing. To remind you, unit testing is where you separate all the individual parts of your code out and test them individually against known data and known behaviors of dependencies. Most people don't write code that is amenable to easy unit testing without dependencies. Brandon gave a great talk at the last PyOhio I was at, which explains how you can do that. You should watch it. But most people don't do what Brandon said. Sorry. So instead, people write code that relies heavily on dependencies. And when you have dependencies embedded in your code and you want to test them without calling those dependencies themselves, you need to use mocks. Mocks are pretend versions of functions or objects that provide known, fixed behavior for you to reason about and test. Most object-oriented languages have mocking frameworks, but the mocking framework that Python provides in its standard library is very, very different to how mocking frameworks in, say, Java work. And that's because in Python, basically every variable everywhere, including built-ins in the interpreter, including in the standard library, is writable by you, the developer. And if we remember that every module, function, and object is a variable in Python, well, if every variable is writable and every function is a variable, that means you can write your own versions of the functions and inject them where you want to go. And so instead of writing a mock like this new sendMail dummy function and passing it in when we construct, we can instead override the dependency with our mock function and test that behavior instead. I can import a module, change the function, and then it will call this version because I've changed the function. And Python even has frameworks that do this overriding for you in a tractable fashion right there in the standard library. It's called unittest.mock. Unittest.mock has a patch function which allows you to patch any namespaced object with a mock object that you can ask questions of at the end of your test. And patch will undo any changes that you might make once you leave its scope, so you don't accidentally end up calling your dummy after you no longer need it. And so in summary, Python doesn't need this pattern because you can override any objects or any functions that you need to override at test time, no matter where it is, no matter who defined it. And that's not a thing that you can do in other languages. If you read the abstract, I said I'd be talking about threads. I don't have time to talk about threads. You should all go look at async.io. It solves the problems that I was going to talk about. So instead, we're going to look at something a bit different. Iterators. The iterator pattern lets you iterate over custom collection types. You're probably pretty familiar with iterators if you've used Python, and one that you're probably pretty familiar with is the range object. Here's a really bad implementation of Python's range object. It's got a constructor, it takes up to 3 arguments, and it has this iter function here that returns this range iterator object. And the range iterator object will look something like this. It has a constructor that stores the range that we were that it came from, and it stores the current value of the iterator. And then it has this next method which returns the next item in the range, or raises stop iteration if there's no next item. I've also added in this hasNext method down the bottom because that's what Java's iterator pattern expects, and it also makes the next slide a lot easier to read. So you can iterate over this iterator by using a while loop. You can go, while this thing has a next object, you can print the next object. If you're going to use the Python primitives, though, you can use this built-in iter function and look for stop iteration yourself. And even though I'm using Python primitives, this while loop doesn't look like I'm writing very good Python code. That's because this iteration pattern is actually one that's described by Python as an officially supported thing. Python provides you with a tool to consume these iterator objects, and that tool is the for loop. The looping construct takes care of calling iter, calling next, and looking for stop iteration for you. So you might be thinking to yourself, but Chris, isn't this an officially supported Python pattern? To which I would say yes. But the other question I would ask you is this something you would want to write yourself? To which I think you'd probably all say no. And that's because managing an iterator is not actually that easy. You have to think about what's happening inside a loop somewhere else, completely outside the context of that loop. So you have to think about maintaining all this state inside a loop without actually thinking about looping, which is kind of weird and sort of counterintuitive. And your consumer looks like this, but the thing that you're concerned about writing looks like this. So the solution to that is generators. If you haven't seen generators before, they're basically like functions, but they handle packing away state for you when you aren't using them. And so you can instead write an iterator somewhat like this. Not only is it much simpler to write, you also get to think about the process of providing your iteration values in the form of a loop. Now, sure, it's a while loop in this case, but it's still a loop, and it's much, much easier to think about how things are going to behave when the constructs look more or less the same. And generators, once you start using them, take iterators from being something you'd probably write quite infrequently to something you will write a lot of, and it makes your code much more legible in the process. So Python doesn't need explicit iterators because generators are much, much easier to write. And so running with that idea, let's look at the visitor pattern. And the idea of the visitor pattern is to easily perform common operations on all the elements of a collection by passing in an operation and then having the collection itself arranged to perform that common operation on each of the elements. And this pattern has the concept of acceptors and visitors. So acceptors are normally the collection that you're going to do the common operation over, and visitors are the operations themselves. And so here we have a generic sort of tree-type data structure. This could be anything you want to traverse, like a directory structure on a file system, or a JSON object that's nested. Basically, it has a data object, and it has some children that you can traverse in some way. And so if we're implementing the visitor pattern, we have a method that accepts a visitor operation, this accept method, and makes sure that every element gets visited by the visitor. So we look down the left, we visit ourselves, and then we look down the right. And a visitor will look like this. It has a method that accepts an item, and it performs an operation on it. So as with all design patterns, it exists because something wasn't easy to write in another language. That's the only reason why these things ever exist. And so we need to think, what about it, this commonly used thing, are we trying to achieve? And in this case, what we want to do is we want to separate the structure of some sort of collection from the operation we're performing. And it turns out there are tools for this that Python provides you with. The visitor pattern came about before most object-oriented languages had built-in first-class support for iterators. Like C++ discovered the pattern at some point in the 90s. Java did it at some point, but they didn't make it easy to write your own. It was much, much easier for classes themselves to know their own structure and handle calling the operations themselves, rather than trusting some sort of outside caller to know how to handle all the elements inside an object. But Python, as we discovered like 3 minutes ago, makes it really, really easy to write your own iterators. So instead of writing a visitor acceptor pattern, you just make it easy to get at each element of your collection in turn using an iterator, and then you can perform your operation with a for loop. So much easier, and it's much, much easier to read. So in this case, iterators separate the structure of the collection from the operation you want to perform on the elements, which is what this pattern was trying to do. And it's much easier to recognize that your operation will be performed on each item of a collection because you have something that signifies to users of your library that something is going to happen over each element of the collection, and that's the for loop. And then you also don't have to worry about wrapping your operations in a function or a class, which is actually quite tedious to do in Python. And then if you need to have multiple different iteration methods, like changing the order in which you visit all the elements, it's not that hard to write more than one. And so Python doesn't need the visitor pattern because generators separate the structure from operations, and for loops let you handle those generators. So that brings us to the end of our tour of features in Python. So what did we learn from this talk? You've probably realized, firstly, that a lot of traditional object-oriented design patterns look really, really clumsy in Python. And hopefully you've seen why this is the case. First up, a lot of design patterns exist because there are features in Python that don't exist in other languages. So you should strive to use those features that other languages don't have rather than re-implementing patterns in Python, because those will be unfamiliar to people who know how to use Python. Some patterns exist because more rigid languages have binding restrictions that prevent you from overriding names or passing around functions or passing around modules. And generators replace a lot of patterns that describe control flow and let you convert complicated ideas around handling state or iteration into much more familiar constructs. So in summary, when you're writing Python, write code like you're writing Python. Finally, an ad, our CFP for North Bay Python is currently open. You should all submit a talk or come along. I've been talking about design patterns and Python. I hope you've enjoyed it, and it looks like I have time for questions. Thank you. Questions, comments, or anyone who wants to tell me that I'm wrong? Yes. Yes. So what del does is it unbinds a variable. So you can, if you go del, it will, the most common thing you would use it for is unsetting a key in a dictionary. So if you want to remove a key from a dictionary, you go del square bracket that key. But you can use it to delete any reference you like. In that case, because classes are variables in Python, that you can pass around or do anything with, you can delete that reference, and as long as you don't copy that reference anywhere, then that means that all public ways of accessing that class go away. There is a way that you can still get at the original class from the instance variable, because Python stores a reference to the class that was used to create it inside every variable. So what I was showing doesn't actually work, but once you start doing that, I think you assume a reasonable amount of risk, and whatever happens to you, you deserve. Yes?
So let's say you want to get into the design patterns with Python. Would reading the Gang of Four give you bad habits?
Would reading the Gang of Four give you bad habits if you wanted to get into design patterns in Python? What I would say to that is, sure, you can read it, but you should read it critically and think about whether or not what you're writing feels clumsy once you're writing it. Because as I think I've demonstrated, a lot of the things that you can implement in Python start to look wrong pretty quickly once you do it. So read it critically and then think about how you can do things better, because there might be features in Python that you can make use of. Now, not every design pattern in the Gang of Four is completely obsoleted by Python features, and I've gone out of my way to deliberately pick ones that, to deliberately pick examples where the benefits completely fall apart, and there are better options in Python. But that's not the case with all of them. So And then to finish off what I'm saying, I think reading any engineering text and thing that gives you ideas for adapting will give you bad habits if you don't think about it while you're reading it. Yes.
Like a handful of those from the Gang of Four group that are, they have unquestionable values on Python?
I would need to brain on that. Any examples from the Gang of Four that have unquestionable value in Python? I'll take that on notice and get back to you. Or I can look up a list on Wikipedia to jog my memory. I'll take another question while you're... Yes.
When you showed your alternative to the visitor pattern, it was a done very generator method.
Yeah.
Is that a magic method I haven't heard of, or is that
No, that was me creating a... so one of the things about dunder methods is that it does name mangling on it so that you can't see them when you ask for help on a class. So if it's something you don't want your users to see, it's a good way of making sure that the users think it's worth avoiding. But it's not a magic method. It's just one that I put in there and put dunders on it to make it appear more invisible. Patterns by type. Any more questions? Yeah.
More on that specifics of dunder prefixing for name mangling. When you talked about when you compared Python to languages such as JavaScript and Java, which I know have more ability to actually implement privacy settings in your code than Python, which is all public. That's it. You have no choice. What sort of pitfalls have you seen with people trying to implement privacy in Python through, as I say, obscurity through complexity and other things like that?
What have I seen? What pitfalls have I seen from people trying to implement privacy in Python? Generally, that things don't work once people poke at things that are meant to be private. Generally, have good documentation and say that things are not meant to be touched, and tell your eventual users that things will blow up if they touch them. Because if you can't prevent something, the best thing you can do is give your users full knowledge of the risks of something breaking, so that when they break it, it's their fault. Factory functions, by the way. Factory functions are a good example of a Gang of Four pattern that you can that is indisputably useful, but you would implement them differently to how the Gang of Four suggests you do.
Don't make me single them.
Yeah,
Them to make me single them.
exactly. Sorry? There is a concept of encapsulation, but there's not a concept of privacy. It looks like there's no one else who wants to ask questions, so thank you for a wonderful discussion, and thank you for coming to my talk. Yeah, thanks.